Hi, this is Moser with a quick tutorial on metallic bonding and the behavior of metals. After you've watched this video, you should be able to describe metallic bonding in terms of the behavior of electrons and explain how the behavior of metals is actually a result of the behavior of those electrons in metallic bonding. You already need to know how electrons behave in ionic and covalent bonding, as well as where to find metals on the periodic table. Hey, look at all this pretty shiny stuff. We got things like, platinum, copper, steel, well, we're going to call it iron for the sake of simplicity, aluminum, and gold. We're surrounded by these metals every day in our lives, and we use them. We use the characteristics that metallic bonding gives them to our benefit. So let's talk about what exactly metallic bonding is. When we're talking about metallic bonding, we're talking about multiple atoms of metals being bound to one another. So far we've talked about ionic bonding, where metals bond to nonmetals, and covalent bonding, where nonmetals bond to other nonmetals. But in metallic bonding, we're talking about atoms of copper bound to atoms of copper, atoms of platinum bound to atoms of platinum. You get the picture. This also covers things like alloys, where we've mixed different metals and the atoms of, say, copper are bound to atoms of gold. Okay, so do you remember where to find metals on the periodic table? Yeah, it's, roughly all this stuff. The line gets a little fuzzy over here, so I'm really fudging it. But we're going to talk mostly today about the transition metals. That's the D block. So what is metallic bonding again? Well, in most of the transition metals, we find 2, 3, 4 electrons in those outer energy levels and lots of empty space. Let's think for a minute about iron. Well, here's the noble gas notation for iron. It's argon 4s2 3d6. And remember, in the transition metals, those D electrons act as valence electrons along with the S. Really, the S and D orbitals they're so close in energy that things kind of tend to wander around. It's as though, to go back to our high-rise dormitory metaphor, you're on a floor with a bunch of empty rooms, so you decide to go sleep in a different room every night. Woohoo! It's a party. Because there are these vacant orbitals which are overlapping, the outer electrons become what's called delocalized. And they sort of wander through those outer empty orbitals. We call this the sea of electrons because these delocalized electrons sort of form this moving sea of electrons around the core of the metal atoms, made up of the nucleus as well as the inner shell electrons. The bonding occurs between those mobile delocalized electrons and the little positive metallic nuclei. That's what we call metallic bonding. You might imagine that it looks something like this. We've got all of those little positive nuggets, the central core of each atom, its nucleus, and all around them in space are these electrons. So what we end up with are forces of attraction sort of running in all directions through the material, as every single electron in the material is attracted to every single nucleus in the material. Woo! That's a lot of attraction. What's so interesting is that the sea of electrons model of metallic bonding was proposed long before, well, not long before, but before Rutherford had proposed the atomic nucleus, certainly before we understood orbitals and the quantum model of the atom. And yet it was proposed once we knew about the nucleus and the quantum model of the atom. It all started to make a lot more sense. What an amazing insight. It's because of these mobile delocalized electrons that metals are superior conductors, especially of electricity, but also of heat. If we think about this as a chunk of metal, when you push additional electrons on it, each electron just sort of pushes the one in front of it until you get a nice steady stream of electrons flowing off it. This is what happens when we stick a piece of copper wire up against a source of electricity. Metals' malleability can also be explained by their electron sea. Malleability, remember, is the ability to be rolled into thin sheets, like, everybody's favorite way to wrap up leftovers. Malleability is seen in metals because as you compress a metal, imagine this is aluminum, even though you're changing the position of the atomic nuclei, there are still forces of attraction going in all directions through the material. Remember when we talked about ionic compounds, we said that striking the material results in a shifting of these delicately balanced bonds of attraction, which don't extend in all directions through the material, but are carefully laid out along a lattice. When that happens, these things tend to split. They're not malleable, they're brittle. Try the same thing with a chunk of metal, and it doesn't matter. These things can shift and still maintain those bonds of attraction. Easy peasy, the attraction still exists. Therefore, those thin sheets of metals hold up just fine, thank you very much. This also explains metal's ability to be pulled into wires, or its ductility. Same explanation. It doesn't matter how we deform this metal, we can pull it into wires, we can do all sorts of things to it. It's still going to have those bonds of attraction running through it in all directions. It's really pretty cool. What's interesting, but not so important at this level, is also that metal's shininess is a reflection of the sea of electrons, because those electrons have energy to bounce photons of light, you remember that from the whole particle wave nature of light, off of metals, making them appear shiny or lustrous. How cool! So the characteristics we see in metals at a macro level are actually due to their atomic level properties. Okay, can you describe metallic bonding in terms of the behavior of the electrons, that sea of mobile delocalized electrons? Can you explain how the behavior of metals is actually a result of that sea of electrons? Good. Get going.